Okay, so today now we're going to be looking at new revolutions. What do you notice here first of all? Two of these 7 distinguished people in history who made the entire modern world possible had beards. And this dude, James Clerk Maxwell, these were all brilliant, smart people. Maxwell's theories, some people would imply, grew out of these other brilliant people's theories. And who knew where their people's brilliant theories grew out of? All we know is that we continue to build upon the success of the past to move forward to the future. And that's one of our jobs as engineers, is not just learning the laws that were found, discovered, created by these great people, but learn also how they created them, what inspired them, motivated them, and learn from their passion and inspiration for ourselves to move forward. In this age, starting back, Georg Ohm, the founder of Ohm's law, which is how resistance in a circuit affects voltage and current through the famous E equals IR, where E is voltage, I is the current, and R is the resistance. Same kind of relationship, by the way, for fluids, where pressure equals flow times the resistance. Is that true? Or is it the other way around, that flow equals pressure times resistance? Think about physically what these laws mean and what makes sense. If I have more resistance, do I get more current? Do I get more pressure? And it's important that you don't have to always say pressure or resistance or fluid or flow or voltage, but think through physically what is happening. And many would argue that this is how, in the age when electricity was people were watching things and discovering things and spinning coils of wire, as the mechanisms became available to actually make wire. Was it for musical instruments and then first, and then for bridges? Was it the materials? What's the order of these things happen, and how do they promote discovery? Why is that important? Well, there's new materials, there's new things being discovered all the time. And if you are alert of what's being happening in other fields, you may come to know about some new material or process that gives you an inspiration, an ability to invent and create where others have not created before. All right, so Ohm's law, how resistance affects the flow of electricity. And then Mr. Kirchhoff said, oh, so if I have a circuit, a lot of parts acting together, how does the current flow when it gets to a node or a junction, and there's a lot of different ways it can go? Well, it'll depend upon the resistance in each of these branches. Similarly, what happens to voltage? So in other words, if I have a circuit with a lot of parts, and you have a power source and a ground, what is the voltage across each element? How does the voltage change across elements? That was coming to understand how electricity works. And then Mr. Faraday realized that when you have electricity, you often also have magnetism. If you have a coil of wire, you get a magnetic field. And how does that coil of wire interact then with a permanent magnet? Is that how we get things like motors that spin? And then when you have magnets, what governs what happens to the magnetic field? Where that magnetic flux goes? What channels it? Is there something I can do in my structure to make the magnetic flux go in a certain way so it's focused? So then when it passes through coils of wire, I get maximum torque. So these folks all contributed to understanding of how electricity flows in a machine. And a circuit is just another form of machine. A machine doesn't mean you have to have gears. Anything that does something we will call a machine. And of course, Maxwell brought it all together with light. And when we understand that, and this is your, for example, your basic course in physics that would follow a course in mechanics of motion physics. When you begin to understand that, you can start to design things like solenoids. And even if you don't design the solenoid, but you understand what is inside of here, a better understanding of how it works and what might be possible if you can't find what you need in a catalog, and this type of understanding can help you to start to design your own unit and then go to the manufacturer and say, I think this should be possible. Can you custom make one for me? So to do that, it requires an understanding of Faraday's laws, Ampere's laws, and Gauss's laws. These are well contained in a topic, for example, at MIT, taught as 8.02 physics class. But any physics class you could learn online of electricity and magnetism, for example, will go in depth on these laws. Very simple to understand and apply. So I highly encourage people to make sure you have done your your electricity and magnetism physics class. But we're going to use some of these principles here and some good back-of-the-envelope calculations to help you understand and start to think about how to design with them. And there's some spreadsheets that go along with this lesson that you can use and to do your first-order calculations. Okay? But let's do a little bit of fun with what you can do. The first thing is a magnetic circuit, and how can you use magnets to hold things together? Recall that we had our kinematic coupling units that we showed back in topic 3 on kinematic versus elastic design. And for example, these 3 balls fit in those 3 grooves to very exactly locate this part with respect to that part, but it can fall off. So you could say, well, I'm going to go ahead and put bolts in here and tighten the bolt down. But if I want to have something that comes on and off, but when it's on, it's very stable, how can I do that without having to tighten a screw every time? Well, if I put a magnet between this part and this part, I could bring it together and it would snap in place. For example, if I took these 2 motors and they have a permanent magnet in them, this motor is very accurately positioned with respect to that motor, and it's the magnet strength that holds it together. Now, this is a stray magnetic field that's doing that. Ideally, no magnetic field would leak out of the motor casing, and you wouldn't have, this would not even happen. Okay. You can design a magnet to have a lifting strength. So for example, I could have an actuator that comes in, a magnetic actuator, comes in and goes to a plate I want to pick up, and it won't pick up the plate, but when I apply a current through a coil, it will generate the magnetic field that passes through the center of the coil. That magnetic field wants to complete a circuit. It wants to flow from north to south, just the way when you have voltage in a system, it wants to go from positive to negative or positive to ground. So the circuit wants to flow, and it'll find a path, flow through the path, the object to be lifted, back and to complete the circuit. That's what this blue line is. That's the beauty of magnetic fields, is they behave essentially like voltages. In a circuit, you get a magnetic circuit, there's resistance to flow of the magnetic field in the circuit, and like for example, an air gap creates a large resistance to flow. You can design your electromagnetic lifter using some of the spreadsheets we provide. It's based on the theory that's presented here. The key is understanding how the force is affected by the different physical parameters of the system. Understanding what kind of steel you need to use in order to make it easier for the magnetic flux to flow through the system and create that attraction force. So a magnet need not be just a permanent magnet that only has one sticking ability, you could turn up the voltage and vary the force and get just what you want so you don't break anything. A permanent magnet will always want to stick. So you can design a permanent magnet so when it gets close, flunk, and that becomes an instability. You can also design the permanent magnet such that it comes close, it doesn't really stick hard, and then you turn a lever and then it sticks hard. For example, a magnetic base for a dial, holding a dial indicator. Play with a magnetic base and try to figure out what is being done. How with a lever can I make this permanent magnet system not have any holding force, and then turn the lever and all of a sudden make it have a very strong holding force. Imagine, I have to turn a lever, and I know from my earlier understanding of the theory that the strength of the magnetic attraction is a function of this air gap. How do I make a big air gap, or effectively a big air gap, by turning a lever? So I bring the thing, the permanent magnet holder gripper in contact, and then turn the lever to make that air gap go away. You can imagine a whole bunch of mechanisms that can make that happen. How would you design, for example, a robot that can climb around inside a pipe, on the outside of a pipe, or on the ceiling and around, if there would happen to be a metal pathway? Why would you want to design a robot that can crawl up the wall, on the ceiling, and around? Maybe you wanted to design a robot for use in hospitals. We worked on these robots that we called the Magnabots, and her name was Maggie. And that was just what that system was for, actually, would be for automating delivery of things in hospitals. And our idea was robots that are driving around on the ground on wheels. The problem with that is if that robot bumps into a person, it can be bad. So we thought we'd go on the ceiling. There's the issue then, what happens if someone knocks this thing and it falls in your head? That's an issue. What other issues are good and bad about having robots roving around on ceilings? Okay. So that's also an important part of product design. Our focus for the immediate future right now is on these wheels. How do you design magnetic wheels? How did we design them? Well, what happens is, and the way we thought of it was, we need a magnetic wheel that can stick to a piece of metal. Here is the wheel. And what does the wheel have to look like? What does it have to do? So remember, north, south. We have to provide a path for the flux to go. Steel, steel. Okay, so the flux goes into the wheel, down, can't go anywhere, can't get anywhere. What do we have to do? We have to have a thick enough sheet of material, so this would be gravity here, such that the flux go around, back up into this wheel, and complete the circuit. The interesting mathematics of this then becomes how strong will the wheel be attracted? Because if we look at this here, we blow this up. Remember earlier we said the force, the magnetic strength of attraction is based on the air gap. Well, right here at the tip of the wheel, the gap is zero. A very strong force, infinitely small area. The mathematics for this, the calculus, actually proved to be very interesting, because as you go farther out here and you take a little differential slice, you have a larger gap for a small area. So this is where calculus is a very useful tool to add all this force up to predict, if you have a round wheel, how much magnetic force you can use it to attract to the wall. You can see as the diameter of the wheel gets bigger, this gap falls away, it doesn't get as big as fast, and you get more attractive force. You get a really big wheel, you get a robot that's too big to build. So how do you balance these things? This is where the mathematics and the analysis are really important. And in the text is a reference to the paper you can look up if you want to see how we did the mathematics of that. But the important thing is to understand that they can be done, and how these things don't just materialize out of thin air and whoop, materialize. Oh, wow, it's amazing. Well, sometimes they do, but usually not. And that's where the math comes in. Okay, so that allowed us to design this cool Magnabot. It actually came from a design contest we had called Mount Everest once, where we had these steel sheets getting steeper and steeper, and whoever could design the robot to go up the steel sheets did better. Okay? So there's a spreadsheet, which we'll be talking about later, that goes through how do you design this type of permanent magnet actuator. It can all be designed, not, hey, let's try some stuff and make it work. That's often very useful for discovery when there is no basis for a theory. And it's also very useful once you have the theory and you've worked through it to build and test and try and feel. But we want you to try to think about, what do I want, and is there a way to predict what happens beforehand so I can engineer a solution and do it in less time? It's a key thing. Remember, we don't have a lot of time. Next, I'd like to show you an active actuator. Previously, we had basically a clamp or something just to grab and hold. Now let's zoom in and look at a solenoid. Okay, so here I've got my friend Mr. Solenoid, and the way a solenoid is made, it's got a core, which is just a piece of very soft iron that a magnetic field loves to flow through. And inside of here, you can't see it, but there's a thin plastic liner. And the other side of the plastic liner is a big coil of wire. The plastic liner is such that when the core is in and it slides with low friction, it doesn't rub on the coil. And the purpose of a solenoid is when I apply a voltage into this coil of wire, a magnetic field is induced that then is attracted to the core. So then I'll have the magnetic field from the coil acting then on this on the core to pull it back in. And there are solenoids that are designed to push. The pull solenoids are much more efficient. So I have a little voltage supply here, and as I turn on the voltage, goes in. Now, I'm going to reverse the polarity and let's see what happens. So I'm going to switch my leads. And who votes for in versus out? Still in. Why is it always in? Why is that? Can I design a solenoid such that it can go in or out? Or must it always be in or out? How do the locks on your car work, the electric locks? So I push the little button and the locks go click up, and I push the button again, they go click down. Is it a solenoid? Is it a little electric motor? How does that work? Go look that up. Take your parents' Lexus or Mercedes or Chevy something apart and really discover the excitement of engineering, especially if you don't put it back together. It really helps you as a track team star, because you can run real fast away from your old man as he comes out. Hey, you took my car apart. That never happened to me, of course. So go and explore it. Where else are solenoids used? Why would you use this thing? All over the place these things exist. One of the lowest cost ways of getting motion. Unfortunately, very nonlinear response. By nonlinear, I mean when you play with this, here I'll increase the, I'll give it some voltage, and now we'll hold it down. I'm putting this in, and it pulls a lot harder when it's almost in. than when it's out. Here I can move it pretty freely, but as I get in close, it really snaps. It's a very nonlinear force that you're going to get from a solenoid. You are not going to get force distance where here it's all the way pulled in and the force is high. It doesn't look like that. It looks more like that. Okay? Is that a problem or not? Maybe you use high force, little bit of motion with a lever to act as a transmission to give you a lot of, not a lot of force, but a more modest force acting over a longer distance. So transmissions can also be used to smooth out or even out the response from some of these actuators. So don't forget about using your transmission with your actuator.